Hello everyone, my name is Icey from Imperial College London. In this video, I'm going to present the RUTH Gripper, which can achieve systematic object-invariant prehensile in-hand manipulation via reconfigurable underactuation. This figure illustrates the proposed gripper's capability. The RUTH Gripper decouples grasping and in-hand manipulation by exploiting palm reconfiguration and self-adaptiveness of underactuated fingers. With this gripper, the motion of the grasp object of different sizes and shapes from one pose to another is straightforward and systematic, since an object-invariant map between task space and joint space can be easily pre-computed. Here is the structure of this video. With the rising interest in robot hands as an approach to achieve tasks in robotic systems, not only robot grasping, but also in-hand manipulation has become an important and essential ability to improve dexterity. Here are two example hands that increasing the hand dexterity by adding an extra degree of freedom on the proximal joints of an underactuated robotic hand. However, in these cases, the control simplicity that underactuation gives to grasping is not maintained when performing in-hand manipulation operations. In this paper, we propose this three-fingered underactuated reconfigurable palm gripper. A 5-bar linkage was selected for reshaping the gripper palm as it allowed three specific points, namely 5-bar joints 2, 3, and 4, to be repositioned in the XY plane through the control of only two motors. A cross-section of the expanded 5-bar linkage showing the tendon routing for the three individual tendons is shown. Each of the tendons will pass through the 5-bar mechanism, ensuring no horizontal translation occurred across the 5-bar joints axis, which means a decoupling the 5-bar degree of freedoms from the flexion degree of freedoms. Also, using the 5-bar structure, we can reposition the fingers to allow for a variety of grasps. Parallel grasp is ideal for pinch grasping small objects and planar grasping regular cubic objects. Trigonal grasp is ideal for power grasping spherical objects. T-shape is a combination of both the parallel and trigonal planar grasp, in that it can perform power grasps on the majority of objects, with an increase in performance grasping regular cubic objects. Here is the gripper grasping performance for different objects. The feasible grasping workspace of the gripper is the set of positions in which an object can lie relative to the base of the hand, the palm, and be successfully grasped. The blue points are the XY manipulation workspace of the RUTH Gripper in respect to the 5-bar mechanism and gripper housing. 5-bar joint position of joints 2, 3, and 4 are also shown in yellow. It is possible to achieve a range of different grasping positions, as the 5-bar linkage can be reconfigured such that the center point of the proximal joints of the fingers is moved underneath the position of the center of the object. Technically, the feasible grasping workspace is the same as the in-hand manipulation map. The path planning algorithm is based on lookups through the pre-computed configuration tables, and then send the configuration to the motor in a constant discreteness. For testing, we selected 3 different trajectories shown in 3 different colors. These two figures present the different views of the manipulation map with the 3 trajectories. The trajectory 3 is a pure rotation trajectory, the trajectory 2 is a pure translation trajectory, and the trajectory 1 is a random trajectory. We selected those 3 different types of trajectories to test the gripper comprehensively. Here is the video of the experimental results, showing the gripper manipulated 9 different objects in all 3 trajectories. During the tests, the gripper were given the θ1 and θ2 values produced by the map by input the target x, y, and phi. The change of the θ1 and θ2 during the manipulation are linear. The sample experimental object trajectories are compared to the simulation trajectories. Top left figure shows the summary of the sample experimental object trajectory compared to the simulation trajectories. Right figure shows the translation and rotation arrows of the experimental results of each trajectory on 9 different objects. Different color indicates different objects. The last bright yellow indicates the average arrow of all 9 objects on each trajectory. Left bottom table presents the actual values. The gripper performance on manipulating various objects of different sizes and shapes is similar. The final position arrows may occur because of the changing contact points during the prehensile in-hand manipulation. In the simulation, we assumed that the object is always being grasped at the center of the hand, and the grasping configuration of each finger are identical. However, in reality, there are some aspects that makes this assumption not totally valid. In this paper, we presented the design, construction, and evaluation of the RUTH Gripper, which decouples the manipulation and grasping to facilitate the control and implementation of prehensile in-hand manipulation. Through the use of a 5-bar linkage as the palm of the gripper, the fingers are capable of repositioning to allow not just different grasp types, but object-invariant in-hand manipulation. We explored the design of the reconfigurable palm and how we achieved underactuated constant tendon routing despite the ability of the fingers to change its proximal joint position. We proposed an algorithm to compute the feasible manipulation map using distance-based kinematics, and also proposed an algorithm for path planning and control. From the experimental results, we see that with the proposed mechanical intelligence design principle, the gripper can achieve precise systematic in-hand manipulation, regardless the particularities of the object, with a simple control scheme. For future work, the introduced grasping manipulation decoupling approach can be explored for spatial in-hand manipulation. And that's it. Thank you for listening. Bye.